So let me get this ready. And okay, so hi everyone, and good morning. I'm really happy to be here today, even with things being a bit weird due to COVID, but we'll try to make the most of it. I want to tell you about the projects I've been working on these past few years. They're a bit different from each other, but they both share this title of quantum and nonlinear optics in quasi-1D systems. Or to put it more simply, photons in tubes. And I'll try to explain what that means in the coming slides. I'll first give a wide overview of the topic, and then we'll dive into the experiments themselves. So we want to achieve quantum nonlinear optics, which for the rest of this talk I will call QNLO. This diagram, which I borrowed from Misha Lukin, shows 4 relevant regimes. If we consider weak interactions between photons as is normal, we get linear optics when the optical power is low and classical nonlinear optics when the power is high. But if we increase the interaction strength per photon by some mechanism, we can get quantum many-body nonlinear optics or quantum photon-photon nonlinear optics, which in our lab is where we want to be. An atom is already a nonlinear absorber because it can absorb a single atom, but will be transparent to the second one. But the problem is that it's difficult to achieve strong interactions between a photon and an atom. So we want to develop some techniques to build systems that do show strong few photon QNLO. Now, why would anyone want to do this is a very good question. The spectrum of applications of strong interactions with quantum systems spans this basic science to applied technology gamut. And it all comes down to having new degrees of freedom to play with. And there's a wide variety of applications, from new phases of matter to precision measurement of gravity and magnetism and time, to distribution of encryption keys for more secure communication. But this is all alongside this possibility of universal quantum computation that's attracting a lot of attention. And this attention is manifest at the national scale by these very large billion-dollar projects in the EU and US and China, and also by smaller projects in places like Australia and in Israel as well. This is not purely academic, with corporations springing up around quantum tech, building these products that distribute keys and measure time, or even try to develop fully fledged digital or analog quantum computers. So the vision in many of the quantum tech applications involves a sort of a quantum intranet, a network of interconnected quantum nodes which are able to communicate over a channel. And this is where photons shine, right? Because they can be easily transmitted over long distances without loss of coherence. But photons need not be only the carriers of information, they can be part of the process itself. And if we have photon-photon QNLO, we can create fully photonic quantum gates for information processing. This is shown in this cartoon below. It's a black box which transmits a single photon if a control photon is absent, but imprints a pi phase if the control photon is present. This is a controlled pi phase. But in free space, it's not usually the case that photons interact. So to create interaction, we need to go through some sort of a mediator. In our case, this is going to be an atom in a gaseous ensemble. If you're not from atomic physics, this is what is normally at the heart of this type of light matter experiment. It's a glass cylinder where some atoms are inside and a laser beam or a few laser beams are going through it. And we're interested in what happens to the light as it goes through this medium. When we think of a light interacting with an atom, what we often think of is 2 electronic orbitals or a few electronic orbitals carrying different angular momentum. And because light is an electromagnetic field, it can couple these states, so it can induce transition. The effect of the atom on the light is captured by these curves on the right, representing the real and imaginary parts of the susceptibility of the atom to the external electric field. So the atom can either scatter the photon, this is represented by this blue curve, or it can imprint a phase, which is represented by this orange curve. The absorption of the medium is quantified by this parameter, the optical depth, or OD. And it depends on the atomic cross-section, which is saturated at the resonant wavelength, but also on the density and the length of the medium. But as for the phase that we imprint, turns out that what we're often interested in is the dispersion of the medium, which is the slope of this curve. And as you can see, the slope is strongest where the absorption is strongest as well. So a two-level system is sometimes not a very good thing if what you want to do is get strong back action, but no absorption. I want to try and give us an intuitive understanding of this interplay between light and matter. So a fair mental model to keep is of the atom as a harmonic oscillator. And this is true because the electrons slosh around between these two orbital states under the external drive. And this is called an oscillating dipole. Because we have a pretty good intuition about the harmonic oscillator, we can move forward with this picture. So in this mechanical analogy, the black arrow represents the driving force, right? This is analogous to the light shining on the atom. And the mass and spring system represents this oscillating dipole. This graph above shows how much power is dissipated by the atom from the driving force. And we can see that when we drive this off resonant, what we get is a transparent medium. But if we drive the system on resonance, we do get dissipation and the medium becomes opaque. So the question is, can we get a resonant interaction when the dispersion is strong but avoid absorption? So there's this famous trick called electromagnetically induced transparency, or EAT, which can give us both. It involves another atomic level and another laser. And by using this, we can enjoy the best of both worlds. As you can see here, the susceptibility is now modified. We still have this steep slope in orange, but we have transparency in blue. And this trick works because we're coupling not one, but two oscillating dipoles. So to understand what's happening, we can go back to the same mechanical analogy. Like before, the black arrow represents the light driving the system, but we now have two masses and two springs, and they're coupled by this thick spring in the middle, which represents the additional laser. And such a coupled oscillator system has two absorption peaks, not one. This is called normal mode splitting. And each peak represents another mode of vibration, which is in tune with the driving laser such that it absorbs maximally from this field. So this left peak represents a symmetric oscillation mode of this coupled system. And the other peak represents this breathing mode where the masses are moving in antiphase. But between the peaks, we have a particularly interesting mode. It's interesting because eventually what we see is the red mass moving wildly, but the blue mass not moving at all. And you can see why this happens, because when the blue mass wants to move to the right, this thick spring is in compression and preventing motion. And when it's trying to move to the left, the spring is in tension, so it's preventing that as well. So no power is dissipated from the driving force, and this system will be transparent. From the point of view of the atom, this is called coherent population trapping, but from the point of view of the light, this is EIT. These models are nice to me because they give us some mental framework to think of when we're thinking of these issues. And this is a nice quotation from Lord Kelvin, who seemed to agree with me. He said that, "It seems to me that the test of do we or do we not understand a particular point in physics is, can we make a mechanical model of it?" But this is also true for electrical models. And in the case of EAT, it works with pretty much any coupled oscillator system you can think of. Of course, this is not generally true if you allow for a non-classical description of reality, but I think it's still a nice starting point a lot of the time. In any case, using EIT, we can get dispersion without absorption as we wanted, but we still need some way to toggle between absorption and transparency. And this mechanism needs to be able to do so with just a single photon. So this will come about by adding interactions between the atoms. So now let's discuss atomic interactions for a minute. If you look at low excited states of an atom, the wave function doesn't extend very far. These images show slices of 3 orbitals. This is the orbital, the electron radius expectation value. And these states are identified here in spectroscopic notation. And you can see that they extend to about 1 nanometer away from the center. So unless we're at BC conditions, the density is such that it's very unlikely to be, for two atoms to be in such close proximity. So the atom-atom interaction strength is very low. And because there's low interaction strength between the atoms, there's no strong interaction between the photons. So instead of looking at these low-lying excitations, we can think of highly excited atoms, Rydberg atoms, where we place the electron at the high orbital, large n. And because the electronic radius scales with the square of the atomic number, we can get these atoms which are almost mesoscopic in scale. They're not nanometers across, but microns in the case of this rubidium atom in the 100s state. And an electron that distance from the nucleus is very, very weakly bound. So small perturbations are now becoming important. The way the atomic properties of Rydberg atoms, such as the orbital radius and the radiative lifetimes and the polarizability scale, make all the properties of Rydberg atoms very exaggerated. This gives us a sensitive knob to modify the system. And this was described in a recent review paper as Mother Nature's most tunable quantum system. And to get a sense of how these scaling relations affect us in the lab, I want to showcase the effect of having an atom with a very strong polarizability. So this diagram is called the Stark map, and it shows how the energy levels of an atom shift under the influence of an external DC electric field. This map in particular was drawn for the Rydberg 92S state that you can see here in the black line in the middle. And you see that the image divulges very quickly into the spaghetti of lines that's sometimes confusing to understand. So to make sense of what we're seeing, let's see what happens around here at 0.2 volt per centimeter. This histogram shows the composition of the eigenstate at this field in terms of the unperturbed states. So you see, we mostly see this 92S state as we intended, but there's an admixing of additional levels. And as we increase the electric field to, let's say, 0.4, the 92S state becomes not even one of the most important components of the new eigenstates. So and these are very weak electric fields. So if we don't take this into consideration, it will be very difficult to actually excite a Rydberg state, pure Rydberg state. And we had to take this into account in designing the system. I'll say some more things about this later. Just for comparison, by the way, here's a Stark map for a non-Rydberg state. And as you can see at this scale, and these are the same electric fields, it's essentially unaffected. But because these atoms are so sensitive, we can actually use that. And this is the basis of the atom-atom interaction that we're after. This is the van der Waals interaction, which is represented by this C6 coefficient. And it has a very strong n to the 11 scaling with a principal quantum number. This diagram shows the interaction strength in gigahertz as a function of distance. And you can see for 3 different n numbers. And you can see that even within a few microns, we already get an interaction which is tens or hundreds of gigahertz. And the effect of this is the following. If we're trying to excite a Rydberg state in this 2-photon excitation, it'll be fine to excite the first atom, but a second atom that sees this excited state will have its Rydberg state shifted very far away, and it won't be possible to excite it at all. So this phenomenon is called the Rydberg blockade, and it provides us the quantum nonlinearity that we wanted. Here you see the Rydberg blockade distance as a function of principal quantum number. You see that, for example, n equals to 100, we have a blockade distance of about 10 microns. And what that means is that only a single Rydberg excitation can exist in a sphere of this size. All the atoms inside the sphere share this excitation in something called a Rydberg superatom. So the effect of this is that if a photon tries to enter the blockade distance, instead of seeing a 3-level system in transparency, we'll see a 2-level system and will be absorbed by the optical depth of this sphere. So it's clear that the optical depth of the sphere must play an important role in what's happening. And because it plays an important role, it has its own name. It's called the ODB, or optical depth per blockade radius. And to get a sensation of what this means is we can imagine a medium or a blockade with an ODB of 5. And in that case, we will have a single photon causing scattering to a second photon to the tune of over 99%. So increasing ODB is key if we want to see QNLO phenomena. And the ways to do that is, of course, by increasing the principal quantum number, but also by increasing the density, which is exactly what we do in the cold atom experiment. So as I've mentioned, the Rydberg excitation is done with this two-step ladder using two lasers. And though it's not the same shape that we saw before, this lambda shape, this still is, this shape still supports EAT transparency. So we can benefit from both this resonant transparency and the Rydberg blockade mechanism. This is a measurement from our cold atom system. This is an excitation into the 90s state. And in the center of it, you can see this transparency window opening up. To conclude this discussion on the underlying physics, I want to note that if we recall the susceptibility of the three-level system, we can get this interesting insight into what's actually happening in the medium. The slope of the orange curve gives us the dispersion, and this actually sets the group velocity of the photon inside the medium by this equation here. Because the slope is positive, you see that the group velocity is lower than c. So this is called slow light. And you can think about it as, you can imagine a photon going through the medium and exciting atoms into different states in its wake. And this combined photon-atom system has a name. It's called the Rydberg polariton. Because Rydberg polaritons interact through the Rydberg component, this is exactly the framework that we have to describing and designing and thinking about our Rydberg QNLO experiments. So I want to take a very quick detour and tell you about the origins of this story. When we set out to observe QNLO, the lab was still at the birthing stages. When I first showed up, this is what the room looked like. And within a few months, we had a room with a floor, and eventually a room with an optical table. This is the room where I led the design and construction of the cold atom setup. It's later evolved into this never-ending stream of equipment coming in and a slow ramp up into what eventually became our cold atom system. In these pictures, you can see the red glow of the cooling lasers here on the left, taken with some camera tricks, and the cold atom cloud glowing in the very center of this image. This purple glow in the back is due to UV light, which we use both to remove atoms that stick to the walls of the container, but also in this case for dramatic effect. So I want to now go in and speak about what is needed to build such a system and what can be learned once you build it. So this is the main body of our cold atom system. The whole thing from here to here is about 1 meter long. It's about 30 or 40 centimeters tall. And it's composed of a large pump assembly in the rear, where we can connect a mechanical roughing pump and additional high vacuum pumps on top to get the vacuum levels that we need, and a physics chamber in the front, and it's surrounded by optics to get cooling and trapping and probing of the atomic medium. Here we get a better view of the physics chamber. The cloud collects here in the center. This thing is about 9 centimeters by 9 centimeters by 16, so it's like a small fishbowl. And it's about 2 or 3 times larger in every direction than what is common in cold atom experiments. It's all glass, so we have good optical access, and you'll see later why we actually need all this access. And the reason it was selected to be this big, this glass cell, is so we can get the dielectric surfaces away from the atoms. Because as I said before, we're very, very sensitive to any stray electric field when we're trying to excite these Rydbergs. The atoms come from dispensers in the back, and we have an additional viewport. And at the center, you see this ion counting assembly. These 4 golden rods are a lens for ions. And behind this pink element, there's an ion counting device that can be used for diagnostics. So how do we build this? Well, there's this famous Maslow's pyramid in psychology. It tells us about how people need to fulfill basic needs before they can go on to better and bigger things and self-actualize. And in AMO, there's a similar pyramid. This is the AMO hierarchy of needs for mostly for anyone not from AMO. We need to start by building a vacuum system. This is a very infamous process, which can be very painstaking. But once you're done, you mostly you forget how bad it was, and sometimes you want to do it again. Then we need an electromagnet assembly, which sets the shape, well, the direction and intensity of the magnetic field that we need in different parts of the experiment. And we also need to make sure it doesn't get too hot. Then we set up lasers with the correct colors and intensities and beam shapes and whatnot. We then need to build a control system, because all these other things like the lasers and the magnetic field, but also cameras and shutters and different things on the table need to be choreographed. And they need to be choreographed in such a way that you have microsecond level precision over the control of time. This needs to be done with something other than a computer, sadly. So this is often done based on an FPGA system, as was the case for us. And only once all of that is done and everything is in place and well calibrated, and assuming nothing broke in the way, can you actually go and try to do new physics. So I just want to offer some general advice for anyone who might build a vacuum system in the future, just based on my experience. First thing is that if you get a custom glass cell, make sure it comes clean. Our cell had a piece of tape stuck inside it, and to get UHV conditions, everything needs to be super clean. But if you do get a dirty cell, make sure you can use child labor to clean it. In this case, we used Ofer's daughter, Zohal, who very kindly offered her patience and small hands. And one final thing is that if you were able to clean your dirty one-off cell, make sure it doesn't leak. Ours was horribly leaky, and that's not a good way to get a billionth of atmospheric pressure. But if it does leak, we found that with enough glue and luck, you can get a seal going, more or less. And all this vacuum business took about a year, but as I said, once it's done, you kind of forget about it. Then you need the strong electromagnets. Because the trapping mechanism needs a strong gradient, we had to pass large electrical currents through the coils, and therefore to heat them, and they actually have an empty rectangular cross section, so we can pass cold water through them at all times. And once they're running, they produce this quadruple magnetic field, which means it's 0 in the center and linearly increasing on all sides, which is what we need. We then need to generate the correct laser colors and intensities. This is a section of the table which has our red lasers needed for cooling and trapping and probing. But the lasers shown in the previous slide all have similar frequencies. But to get excitations into Rydberg states, what we need is the ability to stabilize lasers with very different colors. And to do that, we use this ultra-stable reference cavity. And it's made of special low thermal expansion glass that's housed in its own vacuum vessel. So this gives us a precise length scale. It's just a very stable ruler to which we can reference the different colors. In total, there are 9 frequency stabilized lasers in this system and 1 free running one. These red ones are cooling lasers. The black ones are dipole trap lasers that I'll discuss soon. And all of the physics is actually going on along this axis where we have the different control and probing lasers. So to get the density high, which I said is an important consideration, we use a dipole trap on top of the magneto-optical trap. It's kind of an optical tweezer, so you have tightly focused, far from resonant beams at where the atoms are. And this is a calculation of the trap depth for the angle and intensity between the lasers and intensity that we have. And if we take an absorption image of the atoms with this dipole trap, once everything is constructed, we do actually get something that looks very pretty much the same, which is nice to get. And at the center of this trap, we have about 10 to the 12 atoms per cubic centimeter at 20 microkelvin, which is what we need for the experiment. So there's now this question of how can we tune our lasers such that we actually select the Rydberg excitations that we're after. So we've developed this simple procedure that enables a high contrast and quick identification of Rydberg lines by measuring them in a running magneto-optical trap in situ. Because the mott fluorescence is very bright, we saw this before with the naked eye. This is, the mott fluorescence is very high, you can see it. If we shine a Rydberg coupling beam on a running mott, what we get is a 2-photon excitation that pretty much destroys the mott trapping mechanism. So this generates these very deep depletion lines with a contrast of over 95%. And we can compare these lines to the theoretical transition frequencies to identify what we're actually doing. But there's actually more information hidden in this spectrum. Because these are dipole transitions, we only expect to see even lines in the spectrum, right? We're starting with an even state, and we're expecting to end with either an S or a D state. But we get additional lines in the spectrum. So what's happening here? And what's happening is that because of the polarizability of the Rydbergs, and because we do have residual electric field in the cell still, we have additional lines appearing. And there's actually a lot more that can be learned from an in-depth inspection of this spectrum. And it's nice that such a simple method that's very easy to implement is able to give a lot of information. And this actually also works in 3-photon transitions that we've tried, and I will tell you about in a minute. So when does this system break down? If you go to very high end states, because the separation between adjacent levels becomes smaller, like n cubed, everything becomes, and also the polarizability becomes higher, everything becomes a bit of a mess. So this is a spectrum taken around n equals to 167, and we cannot identify any of the lines here. So we now have everything we need to run a QNLO experiment. And I'll tell you about how we run that. So we begin by loading a magneto-optical trap that takes about a second. And we then transfer the atoms into the dipole trap to increase the density. But sadly, we cannot run the experiment inside the dipole trap because there is the light shift that the atom experiences inside the trap is not uniform. So we do the next best thing, which is to strobe the trap, and we have 10 microseconds off, 10 microseconds on. While when the trap is off, we can probe and collect our data. And we do that for about 10,000 cycles. And that supplies us with maybe 10 or 100 milliseconds of data each time. In between mott loading cycles, we can change a parameter like the detuning or intensity of the probing beam. And this gives us the experiment. I now want to show you a little animation that I've made that shows an artist's perception of what's happening. So we begin by loading the atoms into the mott. These red beams are the mott cooling beams. The purple beams are the dipole trap. Once the red beams are off and the magnetic field is off, we have this dense medium in the dipole trap. And we can start our probing and recollection cycles. This is not an entirely physically accurate picture, I must say, but it gives an overall picture of what's happening. I hope this helps. This is what an EIT spectrum looks like to the 101S transition in our system. What you see in the vertical direction is the detuning of the probe, and along the horizontal direction, this is how this spectrum evolves over time. And I've made these 3 cuts so we can see more clearly what's happening. And these cuts represent these three EIT spectra, which we already know and love. And you see that the spectra drift upwards as time progresses. And the reason for that is that atoms are leaving or escaping the trap as time progresses. So as atoms are leaving, the OD is decreasing, but we still have a few tens or maybe hundreds of milliseconds, as I said, where we can collect data. But what we want to do is not to see EIT spectra. We want to see quantum light. And the way to do that is to sit on top of one of these peaks and collect statistics of light. And this is the way we do that. We use this Hanbury-Brown twist configuration where we don't have 1 detector, but 2. And these are click detectors. So the only information they give us is that and a photon has arrived, but nothing else. And we put a beam splitter before these detectors such that the input is evenly balanced between them. And we then look at the correlation between the arrival time of photons. So this is the G2 intensity cross-correlation function. And it turns out that any statistic of light that's classical can give a G2 of either 1 or above, but non-classical light will generate a sub 1 G2. And there's a simple way to understand that. If you imagine just a single photon coming to the beam splitter, it can do one of two things. It can either go to N1 or to N2, but it cannot go to both. So at zero time difference between the two detectors, there must be anti-correlation. And this is what G2 is indicating. So seeing any G2 as less than 1 is a smoking gun for non-classical light. And because we start with a coherent light source in our system, a very weak laser, the only thing that can modify the photon statistics is the interaction of the Rydberg polaritons inside the cloud. So we performed this measurement at n equals to 70, and we got non-classical light, but it was quite a disappointing result. And the reason for this is that to be able to see this non-classical statistics, we need to make sure that all the photons are actually going through the blockaded region. So we need to get a nearly diffraction limited spot from about 60 millimeters away. And this is a relatively long working distance. If you look for an objective lens with a working distance of 60 millimeters, it'll be very difficult to find one. I couldn't find one. I don't know if they exist, but I couldn't find one. And additionally, this glass cell is introducing spherical aberrations. So that makes it more difficult to focus well as well. So what we did was to redesign this probe path using a few lenses, but the last lens was this diffraction limited, specially polished lens. And using this redesigned path, we were able to get our long distance, almost diffraction limited spot with a waist of 3.5 microns from 60 millimeters away. And here I really want to thank our good friend and talented ZMAX expert and the organizer of this seminar, Slava Smartsev, for helping us getting this done. So at a 780 nanometer wavelength, this 3.5 micron diameter gives a Rayleigh range of 50 microns. So we have this long, narrow tube where the photons can propagate. And after we reconstructed the probe path, this was around April, just at the height of the previous quarantine, we finally were able to convince our photons to keep their social distancing. This graph shows the change of transmission on EIT peak as a function of the input rate. So what we're seeing here is that we increase the rate of input photons, or just the intensity of the probe, and what we see is a decrease of the transmission. And this occurs because on average, our polaritons are now closer together, and due to then the Rydberg blockade mechanism becomes more effective, and they no longer experience EIT transparency. When we measure the G2 function, we get this nice G2 below 1 curve that we were ecstatic to see, of course, because it finally proved that the system is doing what it was designed to do, and we see quantum nonlinear optics at n equals to 85. Just for comparison, this was our signal from before. So I had this multi-level diagram in one of the previous slides, but I didn't really say why it's there. And I've claimed we have 10 different lasers, but it wasn't clear why. So what we want to do next is to generate another type of polariton in the system. All I showed you so far was this 2-photon transition to S states. But if we use this 3-step ladder, we can generate polaritons which have angular momentum that have L equals to 1. And the susceptibility for this transition looks like this. It's a bit different from what we had before, but not so different. We have 3 peaks instead of 2, but we still have these slopes, and we still have the transparency windows. So all we need to do is to work inside of one of them. So we start by shining just 2 of the lasers and scanning the probe detuning, and we get this 2-photon transition into the D state. The transition state strength is much stronger than what we had into the Rydberg state. So we have a very wide transition that we can make hundreds of megahertz wide with just a few milliwatts. This is a scan of the intensity of the control from hundreds of microwatts and up to a milliwatt or so. and this generates a very wide Otler-Town splitting or normal mode splitting of these levels. And if we add our third laser at 1260 nanometers, we can open a transparency peak inside of one of these absorption windows. And this shows that we can successfully generate our P polaritons. So we cannot sit on this peak and measure the same QNLO effects that we saw before, both the nonlinear intensity dependence and this non-classical statistics. As you can see, it's not as deep as what we had in the S polaritons before. And the reason for that is that the C6 coefficient actually now depends on angle when you have angular momentum. So we're still working on optimizing this by controlling the relative direction of the external electric field and magnetic field to that of the excitation laser. But where am I going with this, right? Why do I need two flavors of polaritons? Apart from just to be able to say that I did it. Well, the idea is to access a different kind of interaction between them. If you have SS polariton interactions, all you get is this blockade type of interaction that we described. One polariton going through, the other one being scattered. But with SP interactions, you can get resonant dipole-dipole interaction. So if we get these two polaritons going one towards each other, they will change position. And this will be accompanied by a pi/2 phase. And you might say, well, it looks like nothing happened, but this is just something that looks like an avoided crossing, right? There's an interaction, and because of the interaction, there's a phase as well. So this would give us a robust absorption-free controlled pi/2 gate. And what we plan to do with this is to demonstrate the gating, but also to generate more complex states of light where we create entanglement between many pairs of photons, something called a cluster state. So to summarize this part of the work, we've constructed this system that's able to generate a cold and dense atomic medium. We've generated multi-photon Rydberg excitation in the medium, and we've achieved quantum nonlinear optics with G2 of 0 is much less than 1 for both S and P polaritons. So this work was done under the supervision of Ophel, of course, with these wonderful people in the lab. Really a great lab. I could not ask for more. With Eran and Tomer and Bankim, and Lee, of course, and Chagai, and special thanks again to Slava. So I now want to speak about a completely different experiment. And this experiment doesn't involve cold atoms at all. And what you see here is basically a stainless steel version of the glass cylinder with warm atomic vapor that I showed you in the first part of the talk. And what we do is insert a specially prepared optical fiber into the chamber and observe the interaction between the fiber and the atoms. And this whole container is enclosed by an oven, but the oven is removed from this visualization so we can see what the system looks like. Our goal is still to get strong interaction between light and matter. The interaction probability is proportional to the transverse extent of the beam on focus and the resonant cross-section, which is the resonant wavelength squared. And one of our tricks before was to get a dense cloud by trapping the atom and getting the Rydberg blockade mechanism to involve many atoms. But what if we don't want to build a trap? Can we still get strong interaction, and can we get to this QNLO regime? Maybe we can just focus very tightly and hope for things to work. But the problem is that the Rayleigh range is going to bite us once more. If we have a 10 micron diameter, we get a 100 micron Rayleigh range or so. So this is a very thin sliver of atoms to actually interact with if we're working with hot atoms. And in the case of QNLO, we actually benefit from the overall OD and not just from the OD. So it would be nice to get something a bit different. So what we can do is use a waveguide. Waveguides are not affected by free space diffraction, but to interact with the atoms, these waveguides need to have some free space component. There's a few ways to do this. One is to use coupling to an evanescent mode, as is done in this work here from Uriel Levy in the Hebrew University. An evanescent mode is what occurs if the waveguide becomes of the similar size as the guided wavelength. And in that case, some of the mode just leaks outside. So in the case of this work from Uriel Levy, what we get is atoms interacting within an evanescent mode of about 1 lambda away from the waveguide. So this is the volume along which the atoms can interact. Alternatively, what you can use as a hollow core optical fiber. What you see here is the cross-section of the hollow core fiber. And this center is actually free. There's no glass here. And it's very large. It's about 50 microns across. But the problem in this case is that you're surrounded by surfaces. And we said that we don't want dielectric surfaces to be so close to our Rydberg excitations. So a hollow core fiber also has its own problems if you want to excite Rydbergs. What we do is we take a waveguide and get it much smaller than the wavelength, about 1/4 of lambda. It's a bit surprising, it's still surprising to me that you can do this and still get a guided mode. But what actually happens is that the mode becomes larger and larger. This graph here shows what happens to the mode field diameter in units of lambda when you get the diameter smaller and smaller. And once this gets below 1, the mode kind of explodes. These two dots on the image correspond to the 2 fibers in the illustration on the left. This fiber is only about 50% smaller than this one, but the mode is 10 times larger. And you can get this extended mode to propagate over thousands of times the wavelength. A major effect of what happens when the mode is large is that the atoms takes a lot longer to cross the optical mode. Because it takes a lot longer, it experiences less of a transit time broadening, right? You can see calculation of an absorption line from a fiber with this extended mode in a small mode, and see you get narrower and more pronounced absorption lines. To make one of these thin fibers, you use a heat and pull method. You put a fiber over a flame and let it melt and pull. There's actually a lot of finesse in how this is done. And I should say, I didn't do any of this at any stage. It was done by our collaborators in Barat Dayan's lab and Arno Rauschenbuld's lab, currently in Berlin. And the resulting fiber has this taper shape, which is necessary to get the mode adiabatically transferred from 100 microns or a few hundred microns and down to 100 nanometers. And to do this, you have to do it very slowly. The adiabaticity criterion dictates about 3.5 centimeters of taper. And the final target diameter is 200 nanometers. And this provides us a mode that's 4 or 5 microns across. We then take this fiber and mount it very carefully on this holder, and then place it inside the vacuum chamber. This is a cartoon of what the evanescent mode looks like, more or less. In this short time lapse, you can see the assembly of the vacuum chamber. It's made out of mostly off-the-shelf components, apart from the custom fiber mount. In the back, you can see Ran and myself wearing face masks and personal safety equipment before it was cool. What you don't see in the image is wrapping the system with resistive heating tape and placing it inside the oven. The reason we need this oven is because the temperature of the walls actually determines the density of the atoms inside the chamber. If we don't have an oven, all we have is the vapor pressure of rubidium at room temperature, which is not very high. This is one of our early fiber insertion attempts into the system. The fiber mount has evolved a bit since then, but it's still pretty much the same thing. What we're doing is playing operation. We're trying to be very delicate and slide the fiber holder into the assembly. And this final step is taking the edges of the fiber and splicing them together with this fusion splicer into a fiber that connects the whole thing into our optical system outside. Now, when we perform a spectroscopic experiment on this first excitation level of rubidium through the fiber, we get this spectrum in blue. The reason we have these 2 dips in the spectrum is because we have both rubidium 85 and rubidium 87 inside our chamber. This is just their natural abundance. And these peaks are separated by about 1.1 gigahertz. The red spectrum we take simultaneously, and it's taken from this free space path. It's a very long path, so we get a high OD, and this peak kind of crashes into the floor. But what's interesting is that there's no visible broadening of the spectrum. What we get is very similar spectra in both free space and in the fiber. And that means that our transit time broadening, if it exists, must be much smaller than the Doppler broadening. And this is very unusual for an evanescent field experiment, and it's exactly what we hope to achieve. Moreover, if you look at the OD of both of these spectra, you see that basically the ratio of ODs is almost the ratio of the tapered section to the free space section. That means that the majority of the field is evanescent. The majority of the mode, I meant, is evanescent, right? So this is exactly the thing that we try to achieve. This we call this a super extended mode that's mostly outside. And even though this mode is super extended, it's still very confined compared to what a Rayleigh limited beam would do. So by measuring the resonant absorption of this probe as a function of the probe power, we can see that we saturate the two-level system at about 35 nanowatts, which is very low power, but it means that the local intensity is very high. But we cannot use this measurement to say how high the intensity is, because we don't know how big the mode is. So we try to estimate how big the mode is directly. We do this by performing this time-dependent experiment. We start by using a strong probe that's above the saturation intensity, and you see that the absorption of the atoms is saturated to some value. Then we very quickly change the intensity of the probe to something that's below saturation. And what we see is that the atoms recover their absorption ability in this time scale of 10 nanoseconds. This is very quick. This is quicker than their natural lifetime. And the reason, what we attribute this to, is that fresh atoms are now entering into the beam, and the excited atoms are leaving it. We can also do the opposite. We can start with a low intensity and increase it to a high intensity. Using these two numbers, we can extract the time of flight broadening. We estimate it to be about 15 megahertz. This is consistent with what we calculated for 200 nanometer fiber mode. It's about 5 microns, and it's compatible. And what is most important for us is that it's compatible with the Rydberg blockade distance. This is why the fiber diameter was selected to be what it is. So potentially, and we hope that it will be possible to conduct Rydberg experiments using this system. Finally, we wanted to see if we can perform coherent manipulations on the atoms near the fiber. And we did this by using this 2-photon excitation into the D state. It's not a Rydberg state, but it's still long-lived. And because these two lasers have close wavelengths one to the other, and they're counter-propagating through the fiber, we get this nearly Doppler-free absorption. And you can see the small EAT peaks opening up at the bottom of the absorption spectra. So if we look at the depth and width, or at the width of this EAT spectrum as a function of control power, we can try to estimate the decoherence rate of this transition. We have a power broadened component here, and we have this base decoherence rate. And we get a 40 megahertz decoherence rate, which is perhaps record low for an evanescent mode type experiment. And it proves that we're able to perform coherent manipulation, which is both necessary for our Rydberg experiments in the future, and it means that the system is compatible with atomic memory type experiments we've done in the lab. So we've achieved strong and coherent interaction of light and atoms in a tapered fiber. The mode diameter was estimated to be compatible with the Rydberg blockade, and we get these narrow and coherent transitions, which are compatible with storage schemes. This work was done under the supervision of both Ofer and Barak, and these are the people who did the work in the lab, with Gabi from Barak's lab doing the pulling, and we have Or and Ran and David, and this was also done with collaboration with Arnaud here. So I've presented to you these two realizations of light-matter interactions in quasi-1D. I've done a bunch of other stuff here, like setting up the student conference alongside Chagai Edry that I'm really proud of, and writing some popular science articles and working with high school kids. And it was all fun and a great part of the ride. I really hope you enjoyed the talk, and that's it for me.
Gal, thank you very much. Now the floor is open for your questions, people. Arno, is it all clear? Arno?
Yes. No, so I have a question. You said that the hollow fiber for Rydberg experiment wasn't good because you're close to surfaces, but you're also close to surfaces with the tapered fiber, aren't you?
Yeah, you're right. But actually, there's a lot less fiber if you think about it. It's a very small. I mean, it's a question of the surface area to volume ratio.
Mm-hmm.
I mean, it's an open question. I'm not trying. It would be very nice if I could demonstrate to you already right now Rydberg excitation next to a fiber, but it's not clear that this will be possible. This is an open question.
Okay. Ofer?
Ken?
I'll try to keep some questions to the next part, but I'll donate one.
You are allowed.
So you showed the two measurements of G2 at 0 time. One of them with the p polariton was like half, and with the s polariton was maybe few percent. Can you comment a little bit what limits? Do you understand quantitatively what gives you these limits? Why not better? And the second part is, what would you need for certain applications that you envision in the future, like making cluster states, making these collisions?
Well,
there are typically different requirements of quantumness to different tasks.
Right. So for the quantitative difference is not very difficult to calculate. You can get the C6 coefficients. Sorry, you can get the difference in C6 coefficients at the same n level, I can't remember it off the top of my head, but even if you maximize the C6 coefficient in the p polariton, it's still about 80% of the maximum with the S state. And to get a maximum in our case, what we will probably have to do is to control the electrical field experienced by the atoms. We suspect that there is some broadening due to non-uniform electric fields. So we don't have electric field control inside the vacuum chamber. We do have external electric field control that we've only added quite recently. So both the electrical field control and the magnetic can both improve things, but they won't improve it to the same level, I don't think, as with S states. As to whether how good it should be, I don't know. The answer is that I don't know.
Hi, Gal.
Alan?
So I'm not keeping any questions for later. So first of all, this was a beautiful presentation on all levels, including in particular the physical intuition you tried to put in every step. I enjoyed it very much. And I have 1.5 questions. So they're not trick questions, which means it's not something you need to know. And I do, it's almost the opposite. So maybe you know, I'm not sure of the answer. So it relates to the EAT spectrum. So you showed this physical model of these weights.
Yes.
And actually, so if you pump it harder, so you know, when depending on the strength of the pump, initially you have an EAT window. And then when you pump stronger, it separates to 2 lobes, and this is the Otler-Towns splitting.
Mm-hmm.
And it's, by the way, the same equations have the same solutions. So this is exactly when you treat a single atom and the cavity, they're the 2 pendulums then are the cavity and the atom. And then the Otler-Towns is strong coupling.
Mm-hmm.
And the EAT window is what is called the bad cavity limit or the Purcell limit. And my question is, so is there a difference So you showed in all of them, in the center, there's the case where one of the masses doesn't move. So that's why you have this transparency window. And it seems like the explanation is good for the Otler towns or the strong coupling.
Yes.
It works for both? Okay.
Yeah, so if the question is whether there's an objective difference between EIT and Otler towns, then there's this paper by, what's his name? Recently deceased.
Dowling?
Dowling, yes.
Oh, really?
So yes. So there's a paper by Dowling that claims that there is a difference, and he speaks about whether there's the information content changes, right? So it's a information theory description.
Yeah.
Personally, I don't
agree,
understand.
I agree.
I don't really. I probably do not understand his arguments fully, and I don't feel that there's a real difference, practical difference in any case.
So I understand his information claim. One of them is a closed system. One of them is an open system. So the Otler towns and strong coupling is where you have coherent oscillations and information doesn't leak this from the system, and the AT window and the bad cavity limit.
So in this paper, they use some metric, some metric that measures the information content, and they show a change, a difference. I couldn't comment further.
Yeah, I was wondering if you can look at the simulation of these two weights and springs and say exactly which is which.
So this is exactly what Dowling does in this paper, right? He solves the coupled oscillator system of equations, calculates this metric, and says yes, there is a difference.
Okay, and the other, so you showed the P. The S2P three photon Rydberg and you showed that it's more complex spectrum, and so there's a similar paper by Gerhard Rempe, again talking about atoms and photons and cavities, and there he claims that the highest slope, so the phase shift, the highest dispersion is always at the bare frequencies. So you look at, so although your system eventually has many normal modes, like you have many oscillators, they all couple, and then you get a complex spectrum, but you look at the places where they cross and have the highest dispersion, that's always the bare frequencies of the original bare atomic transitions. And I was wondering if this is the case here as well. If you always get the highest transition, the highest dispersion exactly on the bare atomic lines.
I'm not sure, but the thing with the S&P interactions, I'm not sure if that's the question as well, but I
was just talking just about the P, just about the spectrum of the P.
So it's all the same physics. I mean, the susceptibility of the 3-level system and the susceptibility of the 2-level system on the transparency peaks looks exactly the same. I mean, especially if you have like the 776 control. If the Otler town splitting is very, very large, of course, there's no, you couldn't tell whether you're in a 2-level system or a 1-level system, 3-level system. So I suspect everything to be the same.
Okay. And once again, thank you for a beautiful presentation.
Thanks.
Anyone else from our visitors? Okay, so with that, I agree with Baraga. You had a great presentation, and let us all thank Gal again. And so now I guess we'll stay in the Zoom room with the committee and say goodbye to all others.
You don't have to go home, but you can stay here.
אז אתה יכול, גל? תחזור רגע לספקטרום של ה-P. לרגע לפני, שזה סלייד אחד לפני שאתה מראה את ה-S2P interactions. כן, אז אולי אחד קדימה.
כאילו יש את זה, את ה-Outlier Terms בלי ה-1260.
עוד אחד.
ויש את זה.
עוד
כאילו יש
אחד.
את הסוסטנטביליות, כן? יש את זה.
כן.
אוקיי.
אז אני תוהה אם ה-highest peak הוא תמיד בול, כלומר, החציית אפס עם ה...